Hello, welcome to a lesson about force and motion. I am happy that I am able to share this lesson which I prepared for middle school children or grade 3 students ages 8 to 9 years old. I gave this talk last February 23, 2022. And so the title is Seeing Further, Force and Motion. You're here listening to this talk because you are curious. You have questions about the world where you live in. It is only natural that you have questions. Perhaps one of the questions you have in mind is, why do we need force in our daily activities? And also, why does motion need force? And how does gravity pull items to the Earth's core? You know, more than 2,000 years ago, the ancient Greeks were a curious people, just like you. And they knew how to explain light because they understood the properties of light. However, they were confused about motion. Fortunately, there was an excellent philosopher scientist by the name of Aristotle, and he attempted to explain motion. You might ask, how did he do that? Well, did you know that Aristotle classified objects according to the four elements in nature, namely earth, water, air, and fire? Notice the arrangement of the four elements. The earth is at the bottom. On top of earth is water. On top of water is air. And on the topmost is fire. And then Aristotle classified motion according to these four elements. Again, notice the arrangement. Aristotle was a keen observer. For example, he noticed that the smoke was rising up and the wood was falling down. Aristotle thought that it is the nature of these objects to behave in such a manner. The wood is an earthly material, therefore it seeks the earth element. The smoke is an air material, therefore it rises up as it seeks the air element. So Aristotle explained that objects move as they strive to get to their proper place. So this is the type of motion that is natural motion, according to Aristotle. And then Aristotle also classified motion according to pushes and pulls. And the following drawings illustrate this. A door is pulled, a box is pushed, and a man is walking. For Aristotle, this type of motion is unnatural because it takes an external object to create the force. For example, notice that the box does not move by itself. In the example, it is the man who is pushing the box. And so, what is motion according to Aristotle? Motion can be classified according to two classifications. Motion can be natural. It is either up or down motion. And the motion can be unnatural. And this is due to the presence of pushes and pulls. The bad news is Aristotle was wrong. But to be fair to Aristotle, he introduced a method of thinking, a way of describing the physical universe. And it is his significant contribution to us, to humanity. Also, he asked important questions, such as, why do objects fall to the ground? Why do the sun, moon, and stars move? Okay, Aristotle's method of thinking starts with a guess, an assumption. And on this guess, his next step and thoughts or explanations are based on this guess. For example, he was wondering why a stone was falling to the ground. And then his guess consists of thinking that there are four elements and the stone was moving according to its nature. Now, it is important for us to identify where Aristotle was wrong. So, did you know that it was his assumption that was wrong? Aristotle couldn't believe that a vacuum is possible. You know, a vacuum. A vacuum is an empty space. In your household, maybe you have that vacuum cleaner where it operates such that it sucks in the particles or things outside, like the dirt, right? So a vacuum is an empty space. And for Aristotle, there is no such thing. So he was assuming that there is no vacuum. His assumption was wrong. For Aristotle, objects move in a medium. For example, a stone falling to the ground is moving through air and it is experiencing air resistance. And when an object is moving through water, the water is the medium and the object is experiencing the resistance of the water. So for Aristotle, things move in a medium and a vacuum is impossible. So take note that Aristotle assumed wrongly. And then enter Galileo Galilei. He was a scientist in the 17th century. He showed what was wrong in Aristotle's thinking. Galileo proved his ideas on motion through observation and experiment. Let me ask you, what is an experiment? Well, an experiment is a step-by-step procedure that starts with a guess and you put the guess into a test and then you perform measurements in order to determine something. And Galileo was famous for his experiment on the Leaning Tower of Pisa. Unlike Aristotle, Galileo found out that a stone that is twice heavier than another stone did not fall twice as fast. Galileo explained that the presence of air resistance makes it difficult for us to see or to observe the true behavior of motion, the true behavior of objects falling down. But if we remove air resistance, then we can observe, just like Galileo, that objects of different weights, when released at the same time, fell together and hit the ground at the same time. In the following table, we're going to look at common observations, and then we're going to ask Mr. Aristotle and Mr. Galileo to explain the observations as though they are in a forum with us. So observation number 1. An object moving across a plane finally comes to rest. Think about the ball which you initially kick and then it rolls to the ground and comes to a stop. So let's ask, what would Aristotle say? He will reason that the object comes to a stop because it is its nature. It is seeking its proper place. What will Galileo say? Galileo would say that it is a retarding push called friction. That's why the object comes to a stop. And then observation number 2. An object keeps moving on a horizontal surface. Think about a person gliding on an ice surface on a skating on a skater. So what would Aristotle say? Aristotle would reason that a push or a pull is sustaining such motion. But for Galileo, he will say that in the absence of push or pull, the tendency of an object is to move forever without slowing down. And every object has this property to resist changes in motion. And we call this inertia. Now, Galileo supported his views on motion with experiment. And so our view on motion follows after Galileo's explanation. Now, let me ask you, is this your first time to encounter words like friction and inertia? We human beings use names and labels as we try to understand our surrounding, our physical world. In this lesson, it is my hope that you will add to your vocabulary the words friction and inertia. Friction is the name we give to a retarding push, and inertia is that property of an object to resist changes in motion. Inertia is an important idea as we look at the person and ideas of Sir Isaac Newton. Sir Isaac Newton was born in 1642, the same year that Galileo died. Isaac Newton was famous for his 3 fundamental laws of motion, as well as the law of universal gravitation. When Isaac Newton was 23 years old, a plague swept through England. And similar to what we experienced during the COVID pandemic, at that time of the plague, people are not allowed to travel nor go to school. And what Isaac Newton did was he stayed at his mother's farm, and he studied. He devoted time studying, and then he formulated his 3 laws of motion. What Newton did was to improve upon Galileo's idea of inertia, and he turned it into his first law. What is a law? It is a rule and then order. Okay? Will you read this with me? Newton's first law of motion, law of inertia. An object continues to do whatever it happens to be doing unless a force is exerted upon it. If an object is at rest, it continues to be at rest. If an object is moving, it continues to move. In the illustration shown, the objects or the people were doing the things they happen to be doing unless a force is exerted upon them. Now, let me ask you, what is a force? Well, a force is simply a push or a pull. And the following are examples of a force. In particular, contact force, when objects are in contact with one another. The first illustration is that of a normal force. So we have a box lying on a table. The table supports the box. and then a man is leaning against the wall. So the man and the wall are interacting with each other, and the vertical wall supports the man. In the second illustration, the cable is pulling on the car. And in the third illustration, friction force slows down a woman as it slides through an icy surface. And then the fourth illustration is a particular example of friction force. It is called air resistance. So as the plane is moving through air, air is opposing the motion. Aside from contact forces, there are also non-contact forces that act at a distance, such as electrostatic force, magnetic force, and gravitational force. Electrostatic force is the explanation to when you feel the sparks as your hand approaches the doorknob, because the charges act at a distance. And when a balloon is rubbed against the hair, it acquires charges so that it either repels or attracts another balloon, as shown in the illustration. And then in the second illustration, a woman is holding a magnetic compass, which is pointing to the North Pole, because the North Pole pulls the compass needle. And then gravitational force, I will explain a bit more about this later on. So children, this is the first rule that governs motion. A force is needed to change motion, but a force is not needed to maintain motion. What do we mean by change in motion? We mean to say that an object is moving faster, or an object is moving slower, or an object is turning to the left or turning to the right, or simply we mean to say that the object is changing direction. Now, in the following video, I would like you to pay close attention to what is happening to the puck as it slides along a smooth surface. To set the puck into motion, a force of hand is needed. A force of hand will give it a small nudge. Okay, we'll push it, and then the hand will let go. And then you will notice that the puck will go on a straight line. So here we go. Okay, one more. The force of hand gives it a small nudge and then lets go of the puck. But the puck just moves on a straight line without turning to the left nor turning to the right, and its speed stays the same. It's not slowing down, it's not speeding up. And so you see that in the absence of forces, the puck continues to move along a straight line without changing motion, without changing direction. And there is no friction because the surface is smooth. Thus, it's a good example where in the absence of forces, an object moves along a straight line without changing motion and without changing direction. Now, did you know that it is possible that more than one force is acting on an object? In the case that more than one force act on an object, what we do is add all the forces, and what we get is a summation, which we call a net force. Shown in the example is force represented as newtons, 5n or 10n, n in n represents Newton in honor of Sir Isaac Newton. So imagine that you and your friend are pulling on an object with the same force and toward the same direction, such as to the right. So the net force is twice as great as your individual forces. Now, what happens if you and your friend are pulling the same object with the same amount of force, but in opposite directions? You are pulling toward the left while your friend is pulling toward the right. The result, the net force is 0 newtons, 0 force. Why is that? Well, you have to think that in the number line, your direction is toward the negative, while the direction of your friend is toward the positive. A negative value, 5n, plus a positive value, another 5n, results to 0. And then let's imagine that another friend comes to join your activity and decides to pull toward the direction toward the right. So now you are pulling toward the left, but your two friends are pulling toward the right. And so the net force is in the direction toward the right. And now we go to Newton's second law of motion, also known as the law of acceleration. Will you read this with me? An acceleration of an object is equal to the net force applied to it divided by its mass. The following is an example of an equation. Acceleration equals force divided by mass. So if you have a ratio such as force divided by mass, what will happen to the result acceleration? If the force is constant, but the denominator, the mass, is increased. The following illustration explains what will happen. In the first drawing, the force of hand accelerates a brick. The brick has mass. And then in the next illustration, you have the same force applied to 2 bricks. This time, you have double the mass. And so the resulting acceleration is only 1/2 as much as the original acceleration. And then in the third drawing, the same force is applied, but this time to 3 bricks. So you have triple the mass, the original mass. And so the acceleration is only 1/3 as much as the original acceleration. Newton's second law of motion is the answer to the question, why can you throw a baseball farther than a bowling ball? Given that you apply the same amount of force to the 2 balls, what comes into play now is the inertia. The bowling ball has a larger mass. Therefore, its acceleration is smaller, and the distance it travels is lesser than the distance traveled by the baseball. And now, let's consider Newton's third law of motion. This is the law of action and reaction. It says that for every action, there is an equal and opposite reaction. This implies that forces come in pairs. Let me ask you, what happens if you punch on a wall? The drawing illustrates what happens. It captures exactly what happens. You will feel hurt. It's because the wall punches you back. And the following are other examples of Newton's third law, or the result of Newton's third law. The recoil of a gun, or the recoil of a cannon. It happens, why? because the cannonball pushes the cannon and the cannon pushes the cannonball. And then in the second illustration, you jump from a boat onto the shore. How is it possible? You push the boat and the boat pushes you. And in the third illustration, we have two ice skaters. The woman is pushing the man while the man is pushing the woman. So we have forces that come in pairs. And then, have you ever wondered how rockets are sent into space? Newton's third law of motion is also an important part there. So the rocket pushes the gas while the gas pushes the rocket. Now I want to talk briefly about the gravitational force, the pull of gravity. The gravitational force is the attraction between two objects having mass. This is seen in a mango falling from a tree, or a planet orbiting a star, or the moon causing tides. Is gravity important? Well, the sun's gravitational force on the Earth keeps the Earth in its orbit around the sun. If the sun's gravitational force is changed, then the Earth might get too close or too far from the sun to support life. Isn't that amazing? That the Earth is in a precise location in the solar system and orbiting the sun. Did you know that the Earth's own gravitational pull is also powerful and it keeps the moon in its orbit? The Earth's gravitational force is also responsible to keep the satellites in orbit, and those satellites send communication signals. We depend on those satellites when we use our cell phones. Aside from the force due to gravity, force as simple as the friction force also allow us to do our day-to-day activities. Without friction force, we won't be able to walk correctly on the ground. Without friction force, the cars will just be sliding and then bumping other cars, unable to stop. So can you think of how force is important when we do an activity as exciting as basketball? So think about these things when you ponder the importance of forces in our everyday. In conclusion, let's read this quote from Paul Hewitt. Newton's three laws of motion are rules of nature that allow us to see beautifully that so many things connect with one another. We see these rules at work in our everyday. Thank you.